Get started here. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class and this opportunity we have just to meet and study your creation. Just pray that you'd give us understanding of series and sequences and some of these results, Lord, today, Lord. In my prayer, Lord Jesus. Amen. So today I have to do some stuff that's a little bit ugly in places, but it's foundational for the rest of the course. So this is my chapter 8. Now, I think Nagel, Saff, and Snyder is excellent on these topics. So, like, if you read the chapter on analysis in Nagel, Saff, and Snyder, you do well. And it has quite a different flavor compared to my notes. So if you read both, you have a pretty balanced pair of opinions on the matter. But anyway, here it is. So I start with a quote. Let's see. This is a quote from Abel, and here's what he said. He says, "If one examines more closely the reasoning which is usually employed in the treatment of infinite series, he will find that by and large it is unsatisfactory, and the number of propositions about infinite series which can be regarded as rigorously confirmed is small indeed." So this was the state of analysis in the early 19th century, right? Before Cauchy and Weierstrass, their work sort of put things on a much more firm grounding. So uniform convergence, for example, was due to Weierstrass, it would seem, and his teacher, Guderman, wrote in 1838, "It is a fact worth noting that the series just found all have the same convergence rate." So even like the terminology was still being formed at that time. That's sort of a early form of what we now call uniform convergence. We'll look at today how uniform convergence is important and what it does for us. But anyway, as is usually the case, this is not completely due to Weierstrass. There's different people who did different parts, and I think sort of the development was parallel because all of these developments were prompted in one way or another, in part by the rather audacious work of Fourier in the early, like 1805-ish or so. He made some really insane claims about functions and sequences of functions that sort of set everybody on edge. And well, also during the same time period, the foundations of calculus were very shaky because they were still done in terms of these things called fluxions, or infinitesimals, really. And so the epsilon delta stuff that you guys know and love and take for granted, it was all sort of just coming into existence at this point, from a mathematician's point of view at least. So anyway, just to give you an overview, we are trying to give a careful definition of some things like sequences and series. All right, so I defined sequences in an earlier chapter, so I won't belabor that. Like the definition of a sequence is, if epsilon is greater than 0, you can find n in the natural numbers such that if n is beyond if little n is beyond the big N, then the modulus of a sub n minus the limiting value is less than epsilon. In other words, a complex sequence converges if you can go far enough out in the sequence such that the distance from the nth term in the sequence to the limiting value can be made as small as you like. All right. So a series, on the other hand, is an infinite sum, right? And a series is said to converge if the limit of the sequence of partial sums converges, right? So we define the convergence of a series in terms of the convergence of the corresponding sequence of partial sums. This is, of course, calculus 2, which you guys, when you take calculus 2, fight. Like, in calculus 2, I always have the feeling with a class in calculus 2, it's like they're like, "We dare you to teach us something. Like, you guys will fight me. You just fight tooth and nail to not learn the definition of series and its convergence." Like, it is so annoying. But anyway, there's its definition. And once you have that definition, it's easy to prove properties. Like if we have two convergent series, the series of the sum is the sum of the series, and you can pull constants out. And these are nothing more than simple consequences of the fact that like the limit is additive and you can pull constants outside of the limit. So like the proof is just this. Here's a partial sum for A, partial sum with the coefficients B, and if you look at the sum of AJ plus BJ, you get just Sn plus Tn, but if Sn goes to A and Tn goes to B, then Sn plus Tn goes to a plus b by like additivity of the limit. Let me scooch down here a bit. So, like I was just saying, this is the nth partial sum of a plus cbj, and so I can pull the c out, and properties of finite sums give me this. But if this goes to a and that goes to b, then this in total goes to a plus cb, which is tantamount to saying that we have the sum law and the constant pulls out law for series. All right. Nothing hard here, and nothing really. So far, there's nothing different about the arguments I just gave in complex analysis as they would be if I was teaching Math 132. I give exactly the same arguments in Math 132 to prove these rules for series there. I do take a lot longer to say them, though. All right, so next up, if you have a complex series, it can be written in terms of its real part and its imaginary part. All right, and if the real series, so if the series formed from the real part and the series formed from the imaginary parts, if these are separately convergent, that's going to be the case if and only if the complex series as a whole is convergent. So we can break convergence of a series into the question of the convergence of the real part and the convergence of the imaginary part. And in other words, and more than that, if they do converge, then this is the result. Like the complex sum is the sum of the real series and the imaginary series, like that. As with many other things, this is a consequence of the vector limit theorem. Now, what's up next is some picky real analysis, basically. This is not about complex. This is just about the theory of non-negative series. And so one of the first things about non-negative series, a non-negative series is a series that's a series formed from adding up terms that are, well, not negative. So if you have 0 less than or equal to ak less than or equal to rk, if you have that the sum of rk converges, then the sum over ak converges, and it has to converge to something less. So this is the so-called direct comparison test you remember, maybe remember from Calc 3. Calc 3, listen to me, Calc 2. There's an exciting proof of it right there. Now, so let's return to the question of complex series once more. Like here's how you define the series carefully if you want to. So like, first of all, sum j equals 0 to 0 is just, by definition, a sub 0. Whereas the sum j equals 0 to n of a sub j is defined to be a sub n plus the sum from 0 to n minus 1. And so this simple rule recursively defines the finite sum. So if I want to prove things carefully about finite sums, I can use this recursive definition, right? For example, if I was to try to prove that, like if I had two finite sums, sum over I and sum over, well, I is a bad choice here, sum over j and sum over k, you know? And I want to prove that like sum over j, sum over k is the same as the sum of k over sum over j of some stuff. Like this recursive definition, probably paired with induction, would be the way to try to do that. So I'm not sure exactly how to do that, so I figure I'll give it to Math 200 next semester. See how it goes, right? No? No? Yes? No? Okay. Yeah, it'll be fine. It'll be fine. So one of the fundamental things that every Calculus 2 student should know, but probably doesn't, is that if you have the nth partial sum and you subtract the n minus 1th partial sum, technically this is the n plus 1th partial sum and this is the nth partial sum because I'm starting at 0. I am not going to fuss about this except for that comment. I already regret the comment. But anyway, the difference of the partial sums, right? All that's left is the highest one here, right? So literally, if you just subtract that to the other side, you get from here, this is the definition to that, right? So what this means is that the nth term is the difference of the nth partial sums. This is where the nth term test comes from. See, if this goes to s and that goes to s, right? If they're both convergent, if this is a convergent series, then as the limit as n goes to infinity, this goes to s minus s, which is 0. Therefore, the limit as n goes to infinity of a sub n must be 0. This is the nth term test. So that's the proof of the nth term test. Okay, so there you go. That's the nth term test. That's still true in the complex domain. If the complex series converges, it must be the case that the, you know, an arbitrary term goes to 0 as you go far on out. Of course, as you also hopefully know, it is not sufficient, right? Everything you know about real series still is true for complex series because every real series is a special kind of complex series, right? So everything, all the counterexamples you know there, they're still relevant. Or all the counterexamples you don't know, they still can hurt you. For example, this one, 1 plus a half plus 1/3. You guys remember the name of this thing? This is the what series? No, no, it's not geometric, no. What, P? P is good. Can you be more specific?
No.
Oh well. So fortunately, none of us are ever going to take a subject test in math for the GRE or anything like that. So not knowing like nooks and crannies of calculus can never hurt us. So it's good. What's that? You don't think you are? Man, you need to want to go to math grad school. It will give me more power over you. Rats. This is the harmonic series, also known as the p equals 1 series. This is the quintessential example of a series which is divergent and yet has the jth term going to 0. It diverges ever so slowly, right? To get to like 20, to get to the partial sums getting to 20, I think you have to go to like 1,000,000 terms or something stupid. It converges really, it diverges really, really slowly, but it nevertheless diverges. Anyway, so now this is the geometric series. So if the modulus of z is less than 1, then we can prove that the sum j equals 0 to infinity of z sub n is 1 over 1 minus z. And on the other hand, if the modulus of z is greater than or equal to 1, then this guy diverges. All right? And the proof of the geometric series is something I might put on your next test because it's easy.
Yeah.
It is actually very easy. So we write down the nth partial sum. Okay, fine, it's the n plus 1th partial sum. You got me. But anyway, I'm going to call Sn this. If I call Sn this, then z times Sn is what? It's that, right? Standard argument. We take the difference of zSn and Sn. What happens? A bunch of cancellation, right? Ka-chunk, 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 chunk, 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 chunk. All that you're left with is 1 minus v to the n plus 1. And then if we factor out the 1 minus z and divide by it, we have a stone-cold formula for the nth partial. This is so amazing. In the world of series, it is such a rarity to actually have a straight formula for the nth partial sum, but here it is. This is the formula for the nth partial sum of the geometric series. And as n goes to infinity, this thing blows up if the modulus of z is larger than 1 or equal to 1. All right. And if z is equal to 1, first of all, you can't even do this calculation, right? So anyway, this series diverges by the nth term test if the modulus of z is greater than or equal to 1. And it converges to this if the modulus of z is less than 1, because as we take the limit as n goes to infinity, this piece goes to 0, which just leaves us with that. All right? So that's that. Now, I mention this again, not as a passing curiosity, but as a warning of things to come. 30–40% of the calculations I'll ask you to do in the remainder of the course are geometric series based. Something like that. It's really important. It's how we create many, many examples. So do keep it in mind for your future calculational needs. Pro tip. Let's see here. A complex series is said to converge absolutely if the series of the moduli converges. See what the difference is? So here we have a complex series. This is actually a real series, right? Because we're taking the sum of the lengths of the complex numbers, right? So this is, in fact, a non-negative real series, which means it's subject to all those special theorems that are true for a non-negative series. Chief among them being the direct comparison test, I suppose. But anyway, so here's a theorem. If we have absolute convergence, then the series converges. And not just that, the modulus of the sum of the series is less than or equal to the sum of the absolute values of the series. And of course, understand absolute value, I mean modulus, right? And here's the proof. So if we suppose that this converges, we're going to assume that, right? It's if-then proof. We're going to let a sub k be xk plus iyk, where these, of course, are real. And notice that the modulus of AK is equal to this, which of course is greater than or equal to the absolute value of xk. And likewise, the modulus of AK is greater than or equal to the modulus of yk, right? So we have this is less than that. Hence, by the direct comparison test, the series formed by adding together the absolute value of x converges, right? So by direct comparison test, we have that this converges, and it has to converge to something less than that. And the same argument goes for the imaginary part, all right? And then I have to rely on some calculus 2, which I don't feel like doing here because it's just kind of grungy. It's not entirely easy to prove, actually, but it's not that hard either. But real absolute convergence implies convergence, right? So if I have absolute convergence of the series formed by xk, then I get convergence of the xk series. And likewise, if I have absolute convergence of the yk series, then I get convergence of the yk series itself, right? So these exist separately. And then by the previous theorem we had, the complex sum of those also converges to, like this then converges to the sum of that plus I times that, which is to say that the, yeah.
So if either one of them didn't converge, we just is automatically convergent.
Yeah, if the real part converged but the imaginary part diverged, game over, not a convergent complex series. And if it's not convergent, it won't be absolutely convergent either. So that's impossible in our current context because, like, if either the xk or the yk is blowing up, if you think about it, that means that the modulus of, xk plus iyk is also blowing up, right? So, yeah. Okay, so next up here. Oh, at this point I'm feeling guilty for using the I'm feeling guilty for using the proof that absolute convergence implies convergence for the real series, given that many of you probably have never seen the proof of it. So here's a proof of it. You take a series, a real series, you divide it up into its positive and negative terms. All right, so Pn the positive terms, Qn the negative terms. And then I slap a minus on the negative terms to make them positive. And notice that the sum of the absolute values of xn are just equal to, well, my bad. I've lost track of what I'm doing. So I have xn is equal to Pn minus Qn. And then I have that. And then I can use the direct comparison test to get this. Anyway, my heart's not in showing you this at the moment, so I'm going to go on here. Well, if I could do both at once, that'd be handy. Come on. Well, let me hang over the, hopefully let me hang over the edge here. Oh, man. All right, hence the absolute value of xn converging implies that the sum of the qn converges by the comparison test. And also the sum of xn converging implies that the Pn minus Qn, well, but then this is that, which then gives me, I'm sorry guys, I mean not. The point is this is standard real analysis that you never saw, all right? So, and if you're wondering where I got this proof from, oh man, it's J? Where was that? What's that J for? Golly, guys. What's this J for? How do I find that? Is it at the end of these notes? What was it? JO2, was it?
It's not James Stewart, is it?
Doubtful. Ah, yes, Johnson, Baugh, and Pfaffenberger. Everyone knows these. Foundations of Mathematical Analysis. This is actually a really useful thing to have sitting around. It's a Dover book. It's about like $10 if you buy it used. And it is it's quite detailed. Like this is definitely a good book to have sitting around. I have used it a number of times. It's one of the more popular Dover books ever made. It's sold tens of thousands of copies, that book. Now I need to find my way back. Where were we? Whoa, that was actually kind of close. Johnson, Bow, and Pfaffenberger. All right, anyway, going on here, guys, as that is not really at all the point of this course. So next, an example. So we have, look at the sum over zj, all right? And so if the sum is not adorned, we assume it starts at 0, just as a default here, guys. All right, that way we save ourselves some writing. And zoom in a bit for the people who are not here. So the modulus of 1 over 1 minus z is equal to that, which is less than or equal to that, all right? I mean, I'm using the theorem we just proved, right? Which is that if the series converges, well, I guess I'm not using that. Goodness gracious. I guess I haven't proved that, but that's pretty obvious. I should make that a homework problem. Prove that. Prove that if the series converges, then the series formed by the, oh man, goodness gracious. I don't even have the words right now. So what's going on here is I've got absolute value of the sum j equals 0 to n of zj, right? Z to the power j. And what I'm saying is that's less than or equal to the sum j equals 0 to n of the absolute value of z to the power j. Now what have I used there? Nothing. What did I do? What's that step? What's that called? Well, I think, no, this is more basic than that. Like this right here, what I just did.
Is the exponent supposed to be on the outside of the modulus of z?
Nope, not yet.
Oh, okay.
So to start with, this is just the triangle inequality. That's all. And then, like you said, that a property of the modulus is that the modulus of z to the j is the modulus of z to the j. So this is straight up equal to the sum j equals 0 to n of modulus of z to the j. All right. But the thing is, this is a real geometric series. Right? This is exactly the sum j equals 0 to n of r sub j. Well, it's a partial sum of a geometric series. My point is, in the limit as n goes to infinity, this goes to 1 over 1 minus r. But r here is the modulus of z. So that step there is a combination of triangle inequality for the nth partial sum, passing to the limit of that, and then using the geometric series on the far right up there. So, all right. It's a very based calculation. That was a far right joke there, guys. Let's see here. So this minus that is that minus that, which is just leaving us with the, this is what I call the tail of the series, right? Everything past n plus 1. And then we can factor an n plus 1 out, and that leaves us with this, which then is that. Great. Therefore, we have the following estimate. The 1 over 1 minus z minus the nth partial sum of the geometric series is bounded above by the modulus of z to the n plus 1 over 1 minus the modulus of z. So I say this inequality gives us a bound on the error for the nth partial sum of the geometric series. We'll need this to think more carefully about where the geometric series, how it behaves. Anyway, so moving on here. So the history of absolute convergence, I mentioned if you look at, that's most likely, R91 is almost certainly Reinhold Vermeer's book. Mentioned him before. It's really, really nice. Moving on here. So that was numerical, basically numerical series. But you see already in my example, I'm playing with functions, aren't I? I can't help myself. Like the geometric series, what was z? See, z is a variable in that previous example, right? It could have been, well, anything as long as it had modulus of z less than 1, right? So anyway, a sequence of functions, fn on E. Now here E is like a subset of the complex numbers for us, all right? So a sequence of functions is said to pointwise converge to f if the limit as n goes to infinity of fn of z is equal to f of z for all z in E. This is so-called pointwise convergence of functions. Here's an example. So most of my examples of pointwise convergence are based on like real analysis because it's just easier for you guys to think there. Like this one here. But the definition of pointwise convergence of real functions is just the same. So here we have f sub n of x equals to x to the n on the closed interval 0 to 1. All right, so what happens? As n goes to infinity, x to the n does what? Well, if x is less than 0, x is less than 1, you've got a number less than 1 and greater than 0 going to the n, going to the infinite power. Let's take a half times a half times a half times a half times. It goes to 0. So we get 0. But if we have 1 to the n, well, that's strictly equal to 1. So as n goes to infinity, we have 0 for these cases, and we have 1 for that case. And this is the limiting function. It's a kind of weird function. It's identically 0, right? Except for 1 where it's 1. There's a lot to see in this example. How about the function f sub n of x equals x to the n on the closed interval 0 to 1? Are these continuous? They are, right? And how about the limit function? Is this continuous? Definitely not, right? 1 is ripped away from 0 at 1. So the limit function is not continuous despite the fact that it's a sequence of continuous functions. So pointwise convergence isn't the greatest kind of convergence because it doesn't always, like maintain the properties of the sequence to the limiting function. Yeah.
Can you explain one more time why the limiting function is not, like you said it was ripped away? Like the one
Yeah. I think the best thing to do is draw a picture. If in doubt, draw it out. Let's see here. Let me draw. So let's draw a graph of like f1, f2, f3, f4. Let's graph them. Yeah. So here's 1. So this is y equals f1 of x, which is just x, right? And then f2 looks like that. Which is x squared, right? I'm going to skip ahead a bit. Here's maybe y equals f10 of x, which is x to the 10th, right? If you take higher and higher powers, if you graph it, it looks more and more like just goalposts, basically. They all go through the point 1, 1. Because like 1 to the n is 1.
Yeah.
But the limiting function, if I can do it in purple, looks like this. So, and then there's an open circle here. And then right here. So that's and so like fn x goes to that as n goes to infinity. So if you want, and this is not continuous, right? Because it's got a jump. Pop. That's what I was talking about. The values at 1 are ripped away. So like continuous, the idea of continuous is that the function has points which adhere to one another. They're not ripped apart. That's basically the idea of continuous.
So for like 1.9 repeating, we kept multiplying that, we would eventually get to 0. But as soon as it goes to 1, it gets to 1.
Well, if it's 0.9 repeating, that is 1. So I almost agree. But let's not have that debate here today. Let me move on here. But yes, if it was like 0.999, stop right there, then that would, if you let, take n to the, let n go to infinity, and that to the nth power, it goes to 0. All right, so next up here, there's another function, which is this. Gn is this right here. And oh man, I should have drawn a picture. Rats. So that one, it's basically n squared. This is a line. That's a line, right? And it's all going on from, so like here's 2 over n. And here's 1 over n. And basically what goes on here is you just have a tent spike, sort of like that. This is, I guess it goes to 1, right? Is the domain set up so it stops at 1, I think? So the way this thing is concocted is so that you've got this like tent, and it's constructed so that the area under the tent pyramid, whatever you want to call it, the area under that contraption there, right? What's it work out to? Well, let's look. Well, let's see here. So the first half gives me a half, and the other half gives me a half. So the integral from 0 to 1 of gn of x is equal to 1 for any n. All right? What happens as n goes to infinity? What happens as n goes to infinity? Well, yeah, that tent becomes a spike, right? And so the area under the graph goes to 0, because the gn, like this, is the 0 function as n goes to infinity. So the integral of the 0 function is just 0. On the other hand, this is identically equal to 1, and so the limit of 1 is 1. So what does this mean? Well, this means that you can't exchange the order of integration and the limit of the sequence here. Even though look, this sequence of functions is converging to something very nice. You can't get much nicer than the 0 function, right? So the limiting function's not anything funky. Like my previous example, like the limiting function was some kind of discontinuous monstrosity, right? Here the limiting function's just 0. Even so, I cannot exchange the order of integration and that limit, right? So these are cautionary examples. They show you that pointwise convergence does not play nice with analysis. Trust me when I tell you that. Well, here's the next example. This one shows you that, what's this one about? Let's see here. Here again, the limit of the sequence of functions is 0. Well, this one, it just so happens that you can commute the limit as x goes to a and the limit as n goes to infinity. So sometimes it works, yay. I don't think this is especially interesting. But the next one, on the other hand, if I look at the derivative of that sequence, I get the x to the n minus 1 sequence. And then if I take the limit of this, I get that. But if I take, on the flip side of things, if I take the limit in the opposite way, I get 0. Of course, 0 is not equal to this. So I'm showing that if we take the limit as x goes to 1 from the left, and if we take the limit as n goes to infinity, if we do them in opposite order, we get opposite. We don't get the same result, is my point. All right? So the limit of the sequence of derivatives is not the derivative of the limit function, is the larger thing to extract from this example. All right, so we have, all right, anyway. So let me stop telling you what we can't do. Let me tell you what we can do if we introduce the more strict notion of convergence, the so-called uniform convergence, all right? Or as the 19th century mathematician called it, convergence at the same rate, whatever that means. Well, it means this. So if you have a sequence of functions on E, we say that this sequence of functions fn converges uniformly to f, all right? If for each epsilon greater than 0, there exists an n, such that when n is larger than n, it implies that the modulus of fn of x minus the modulus of minus f of x is less than epsilon for all x in E. The difference is, with pointwise convergence, you can have a different big N for each x. All right? Whereas here, it's one N, that has to work for all x in the E. That's the uniformity. That's like the uniformness of the convergence. All right? And we don't actually like this definition because that definition is kind of a drag. And as much as this is a course entitled Complex Analysis, it's not really an analysis course, right? Tell the engineers. So we're interested in, finding easier ways to calculate, and this is one of those. And basically, here's the deal: if you can prove that there's what's called a worst-case estimator. So you take the supremum, or you could think of it if you like as maximum. All right, take the maximum of the difference of fj of x minus f of x over x and E, right? You call that epsilon sub j. If epsilon j goes to 0, as j goes to infinity, that's called a worst case estimator for the sequence. And that, if you have that condition, implies uniform convergence. So we're going to see that that's how we actually like to calculate things. And you can prove that if you have uniform convergence, it implies the existence of a worst case estimator and vice versa. All right? So it's another way of formulating the definition. I say, can we show a sequence of functions fn on E is S uniformly convergent to f on E if and only if the sequence of functions is G uniformly convergent to f on E? The G uniformly convergent is my lingo for what's in the red, whereas the S uniformly convergent was my definition. S for standard, G for Gamelin. This is Gamelin's definition. And the answer is, ask Shane. It's one of his homeworks in the other course. So it's half done in the notes that I gave you. But anyway. Yeah, I know. So anyway, so here's a theorem. If we have a sequence of functions on E, then if we have Fn is S uniformly convergent on E, if and only if it's G. So all I'm saying is you have license to use the worst case estimator idea in here. And doing that will save you the trouble of making epsilon n arguments, because you can just come up with a worst case estimator and argue uniform convergence from that perspective. Let me show you. So like this one. So what's the supremum of x to the n minus f of x from x is 0 to 1? Like, what's the maximum that can be? Well, you always have 1 there because you've always got 0 at the start, and you've always got 1 at the end. And that's the biggest the difference between x to the n and f of x can be. F of x is the limiting function here we talked about. So if you just reason through it, the biggest the difference between those can be is 1. That makes 1 the worst case estimator here. It makes it let's say it's the the potential worst case estimator. But it doesn't serve as such, right? Because what's the limit as n goes to infinity of 1? It's 1, right? So that is not uniformly convergent. And I'm saying that's the reason for its bad behavior, all right? Likewise, this one, here, if you look at it, you can work out that the supremum, the supreme value of gn minus g of x. Now, g of x is the identically zero function in this case. And the maximum value that the tent function takes is at the top of the tent. And it just so happens it's n there. So that's the biggest difference. N is the biggest that this difference gets to be. Again, not uniformly convergent, because as n goes to infinity, this surely doesn't go to 0. Right? It's even worse than the other example in that regard. Now, on the other hand, the one that I said wasn't interesting because the limits worked, right? Well, that's the one that's uniformly convergent, because if you calculate the supremum of that one that I kind of rushed through, but if you go back and look at it, you can see that the supremum of this, for that example, in particular x to the n over n, which converge to 0, the largest that is 1 over n. So, because it's largest at 1. And so 1 over n minus 0 is 1 over n. So that the largest this can be is 1 over n, so 1 over n is the supremum. In fact, I don't really need supremum here. You could be writing max, because we're talking about continuous functions with respect to a closed interval, so the maximum value is attained. Indeed, the minimum value is also attained, because we have the extreme value theorem from calculus 1, right? Continuous on a closed set, you get min and max from some place in the set. So anyway, that goes to 0, which makes this an honest to goodness worst case estimator, which is to say that this sequence is uniformly convergent on 0 to 1. So do you see why this is nice? Because we don't have to make any kind of like epsilon n argument. We just do calculus and analysis type reasoning to figure out what the estimator is and then take the limit. All right, so, all right, anyway, so there's that. So one of the important things about a sequence of continuous functions which is also uniformly convergent is that the limiting function is necessarily continuous. So here's a theorem that Dr. Schmidt quoted you in earlier part of the semester. Here's the proof. So if epsilon is greater than 0, by uniform convergence, there exists a big N such that fn of z minus f of z is less than epsilon over 3 for all z and e. However, by continuity of the fn at z at a, there exists a delta greater than 0, such that if we are within delta units of a, we have that fn of z minus fn of a is less than epsilon over 3. So I use the continuity for that. I use the uniform convergence for this first part. All right. So then, if I look at the difference of the limit function f and the limit function at z and at a, then I do this sneaky trick of adding 0, not once but twice, right? And so I have fn minus f of z and fn z minus fn a, and finally this guy over here. And by assumption, that's less than epsilon over 3, as is that, which gives you epsilon, which proves then that the limiting function is in fact continuous at a, where a was an arbitrary point in E. So this is the epsilon over 3 proof of uniform convergence implies continuity. Uniform convergence of a sequence of continuous sum functions implies continuity of the limiting function. That's that. This is not about complex analysis. This is a general truth of real analysis as well. If you have uniformly convergent sequence of continuous functions, we can do the same proof in a much broader context than complex analysis. There's nothing complex about this, let's say. As I was saying right there, this proof is pretty much lifted out of Jausen, what did I say? Jausen Johnson, Bao, and Pfaffenberger. Yeah, that one, page 246. They offer pretty much the same proof for an arbitrary metric space in there. This one, on the other hand, this is complex. Let gamma be a piecewise. What happened?
The back to my earring came off.
Whoa. Okay. Well, hey, I've been waiting for this day. Oh man. What happened to my earring? I had an earring up here all the semester. What happened to it? Oh man. Where'd it gone to? It's not okay. I've been. Here you go.
Oh,
Is this
thank
yours
you.
too?
Wow, it is.
What? Really?
No.
Oh man. How dare you play with my heart like that? You monster. All right, so if gamma is a piecewise smooth curve in the complex plane, and we have a sequence of continuous complex valued functions on the curve, gamma, and if the sequence converges uniformly to f on gamma, then the integral of the sequence of integrals, right, the integral of fj of z dz, converges to the integral of the limit function of the sequence. So what this is saying is that the order of the limit in the sequence and the integral can be exchanged. You can pull the limit of a convergent sequence of functions inside the complex integral. And the proof of this should actually be pretty understandable. Let's see how. So let epsilon j be the worst case estimator for your uniformly convergent sequence of functions. That means that the modulus of fjz minus f of z is less than or equal to that, right? The worst case estimator is the supremum of this difference for z in the context in which we're working. So certainly it has to be an upper bound for any of the values, all right? This is just definition of supremum, basically. So that's the case. And if we look at then, that gives us an m for the ML estimate. So we have the complex integral, the modulus of it is less than or equal to epsilon j times L. But this goes to 0, therefore this must be 0. Because the only way we can have a limit of we have a limit of the sequence going to 0 is if in fact the thing inside the only way I can have a limit of a modulus of something going to 0 is if the something inside the modulus also goes to 0. That's the way limits work. So we find this goes to 0. And once you know that, that implies that this must be equal to that, which is the theorem. So I say, well, this theorem is also true in the real case, as you can read on page 249 of Johnson, Bao, and Pfaffenberger. So it's not, it's more nuanced there because you don't have an ML theorem. You have to do something else. It involves the properties of real integrals, whatever your theory of real integration might be. All right, measure theoretic, probably. But that brings us to our next definition. If we have a sequence, well, in this case, a series, all right, I meant series. This is a typo. This is a series of complex valued functions on E. The partial sums are functions defined as such, all right? And the series is said to pointwise converge if the sequence of partial sums pointwise converges. The series is likewise said to uniformly converge if the sequence of partial sums converges uniformly. This is our standard terminology. Series are given properties as defined by their sequences of partial sums. So this brings us to the Weierstrass M-test, which is an amazing result. And here's how it goes. If you have positive terms, well, non-negative, right? MK greater than 0, and the series of these non-negative terms converges, all right? And if you have complex valued functions on a set E, such that the modulus of the complex functions are dominated by the values of this convergent series of non-negative terms, right? This is called the majorizing series. So you have these upper bounds on the values of the complex functions for all z in the set of consideration. If that's the case, then the series of complex functions converges uniformly on E. This is very nice because we're allowed to exchange the problem of uniform convergence of a series of complex functions for the much easier task of finding a real series which converges and just happens to bound these functions, as I've said, you know? And so here's the proof. We're assuming that the modulus of gz is less than or equal to mk. Let's see, Well, that, of course, this implies, if that's the case, and we have that this is a convergent, the series formed by mk converges, then by the direct comparison test, we have that the series of the moduli also converges. All right. And so then that means that these are that this series is absolutely convergent. Therefore, this series is also convergent. And more than that, I called the thing that the series of GK, I called the sum of the series GZ. You notice that? I'm defining GZ by that equality there. So once I have that, I also have that the modulus of the sum of the series is less than or equal to the actual sum of the moduli, which again is less than or equal to the sum of the majorant series. This is just, again, direct comparison test. So altogether, though, we have a difference between the series and the partial sum. So we can take this minus that, which is straight up equal to this. But by our estimates, that's less than or equal to that. OK? So what that's saying is that you can basically form a tail. Well, the tail of the complex series is bounded above by the tail of the real the tail of the majorizing series. But in real analysis, not real analysis, in calculus 2, a series converges if and only if its tail goes to 0, right? Like the tail of the series is the part that's the end of it, right, beyond. And if you can make the tail go to 0, that's what we need, really. It doesn't matter what happens in the first 200 terms of the series. It's what happens eventually that governs whether or not it converges, right? But anyway, but this shows that the worst case estimator is given by the tail of the majorizing series, and that is by assumption going to 0 as n goes to infinity. Consequently, we have a worst case estimator for the complex series of functions, which shows you that it converges uniformly on E. That is the Weierstrass m-test, which gives us a super nice tool to prove uniform convergence of a series of complex functions. Now, as I was just introducing the notation here, if we have a series of complex functions on E and it's dominated by mj, that means that the modulus of the function is, smaller than m sub j for all z and e. And if this converges, right, if the series of non-negative terms converges, then we call m sub j a majorant for the series, right? They don't have to be unique by any stretch. I mean, you could have more than one majorant for a given series. That doesn't really, as long as we can find one, we're happy. Anyway, this is Weierstrass's m-test, and he didn't really bring a lot of fanfare to this thing, although it's probably one of his more important, like widely spread used. I mean, it is a very important test. And I say he gives this m-test as a footnote in some 1880 thing he wrote. Zur Function, whatever. So here's an example where I use it. The geometric series, right, is equal to this. This is a sequence of complex functions. Does it converge uniformly? If so, where? Well, remember what we derived a little bit earlier today. We derived that the tail of the geometric series, I think that's less than or equal to, right? Less than or equal to that. But you can notice that, so this is a formula for the difference between the sum of the geometric series and the nth partial sum, all right? So we need to be able to find the supremum of this, and it would need to exist and be something that went to 0 as n goes to infinity in order for the geometric series to be uniformly convergent by the Weierstrass m-test. That doesn't quite work for the unit disk. You see why? Look here. So like if if you think about this, how big does this get? If we're looking at, and here we really do need supremum because the maximum doesn't exist. Modulus of z less than 1 is not a closed set. It's an open disk. It's got a fuzzy edge. What happens if your modulus of z is like 0.99999? Not repeating. Then 1 minus 0.99999 is like 0.00001, which, to quote our next president, is huge. So I'm gonna be optimistic. I'm gonna be optimistic. Our next and current president. There we go. Ha, take that, YouTube. I need some shirts. Anyway, so this is not bounded because you can make it as big as you want. Violet always likes it when I bring politics into things. So, you know. So since this is unbounded, no, the geometric series is not uniformly convergent on the open disk, right? However, if you take any closed subdisk, no matter how close to the edge, right, like say the 0.9 radius closed subdisk, it will be uniformly convergent on that because this problem that I just alluded to goes away. Right? If this can only get to be 0.9, the biggest this can be is 0.1, which makes 10 the supremum. Not 10, but 0.9 to the n plus 1 over 10, I think, whatever that is. Because the biggest this can be is 0.9. So you end up with like a 0.9 to the n plus 1 as its like supremum. The point is, if you consider any closed subdisk, or even open subdisk, where r is less than 1, then do I have actually written here? Well, then, in that context, you have this, right? So the well, I mean, here's the majorant. So I have z to the k is equal to that, which is less than or equal to r to the k in this context, right? But this is a majorant because that's the geometric series. Therefore, the series is uniformly convergent by the Weierstrass M-test. But I can't do this if we can let the modulus of z get arbitrarily close to 1. Because I can't pick an r which is larger. Like I can't find this r larger than the modulus of z if the modulus of z can get arbitrarily close to 1, right? I can't find some r that's closer than arbitrarily close to 1 that does this argument. So like that's where the argument breaks down. And this is proof that it has to break down because this is actually the supremum on the full open unit disk. So this is an interesting situation. We have not uniformly convergent on the open disk, but we do have uniformly convergent on any closed subdisk of that disk. This kind of convergence is very commonplace, and it's often called normal convergence, which I think I define next. Well, I say the example above explains why the sum k equals 0 to infinity is pointwise convergent, but not uniformly convergent on the entire open disk. Pointwise convergence is just straight up the geometric series result we proved earlier. But that pointwise convergence is not the same as uniform convergence, right? So we have pointwise convergence on the whole disk, uniform convergence only on closed subdisks, but not the whole disk itself. This one here, sum k equals 1 to infinity of z to the k over k cubed. Notice that if we look at the absolute value of z to the k over k cubed, that is less than or equal to 1 over k cubed. My context here, again, is the open unit disk, okay? Notice that this is p equals 3 series, right? See the 3? We had a 1 in the other earlier today. Therefore, by the Weierstrass M-test, this converges uniformly on the open disk. What's the difference between this and geometric series? Well, geometric series didn't have this lovely divided by k cubed here. And that makes all the difference. this one does converge uniformly on the open disk.